Wait till you see what there is once we get to the top of this mountain.
Mountains. They're supposed to follow the rules of geology. Look at any map and you'll see them running neatly north to south, right where tectonic plates collide and the Earth's crust buckles. Except, here, it's clear some mountains are just wrong.
So
This
Kai,
would be a nice place to watch the sun rise and sunset.
it would. Shame it was so early this morning, we just couldn't manage it.
Yep.
So Kai,
Yeah.
all of this beautiful view here, it's all Scotland.
Well, not really, but yeah.
You know what I'm talking about?
Yeah.
Yeah?
Plates moving.
Yeah. So physically, we are in Vermont, but the rocks here are all part of a mountain chain that once ran all the way to Scotland. Right now, we're on top of Mount Killington, part of the Appalachian Trail and the Appalachian Mountain Range. And these mountains, the Appalachian Mountains, they are older than North America. But honestly, that is not the weirdest thing about them. Today, we're gonna visit and talk about mountains like this one that are in the wrong place at the wrong time, and frankly, took scientists ages to figure out exactly why.
We're gonna figure it all out while we hike 100 miles of the AT.
Yeah, sounds like a plan.
It's going to take us 10 days to cover 100 miles of the Appalachian Trail in Vermont. And along the way, we're going to look for signs of why this mountain range isn't exactly what it seems. And the first clue showed up right in the first few miles of our hike.
Ooh, hello. We have a wavy rock. Yeah. Do you know how it gets wavy?
Deep underground formation.
Oh, okay. I guess he does know. So, this rock here is, I believe, gneiss. And it gets these wavy lines because it forms deep, deep underground, under incredible pressures, incredible temperatures, 700 degrees Celsius and more. And that's because this whole mountain range that we are standing on. Kai, how old are the Appalachian Mountains?
Very.
How old?
Very, very.
Very, very, maybe one more very?
Very, 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 very.
Okay. That's approximately correct. They are older than North America. This rock probably was part of the oldest part of the mountain. It formed deep underground, was covered by, 15 miles of additional rock that has since washed away. I mean, that's longer than we're going to hike today, Kai. I can't. We're only going about 10. But this wavy line right here is a sign of exactly what we're looking for in these mountains, right? Signs of their age, signs of their deep basement history. The oldest parts of this very old mountain range that form deep underground. Very cool. I better get caught up to my family. They're waiting for me. Ooh, but there's more wavy rocks over here.
The origins of the Appalachian Mountains date back at least 500 million years. The mountains formed in 3 separate tectonic mountain-building collisions, 3 different land masses crashing into what we now call North America, one after another, over a span of about 300 million years. Each one piled the mountains higher. Now, the last collision was when basically all of Earth's land came together into one supercontinent called Pangaea. And when that happened, the mountains in the middle, these mountains that we're hiking today, they had reached their peak. What we hiked was the root system, all the stuff that remains that was buried deepest, that survived hundreds of millions of years deep underground. Everything above it, gone. Eroded over 300 million years and still eroding today.
So, we have encountered our first major obstacle. Last night, it poured rain, and there's also bugs. Bugs are not the major obstacle that is
That's what you think.
stopping us right now. We have bug spray for that. The rain last night was pretty intense. So we're now hanging out at the shelter, trying to let it pass. But it occurred to us, that obstacle is actually the very reason why the Appalachian Mountains look like they do today. So the Appalachian Range used to be as tall as the Himalaya Mountains, used to be these majestic, incredible peaks. So what happened? Where did it all go?
Erosion happened.
Oh, yeah. Water did its thing, right? The rain that we encountered last night, the stream that is right in front of us, right here, that actually is continuing the same process of erosion today. You can see here the trail has eroded. They're building a bridge here so hikers can more easily cross. But there's all this caution tape and redirection. I think the trail used to go here, or the bridge is going to go here, and now it's kind of going over there.
Yeah, that's what I'm thinking.
But all of this is exactly the reason that this range now looks kind of gentle and rolling and not tall, majestic. So all that rock went somewhere, and this is exactly where it went. Ta-da!
Mother, yeah.
It looks like it's clearing. Should we
Don't jinx it.
should we take off?
Yeah, we should.
Continue on? All right. Let's keep going. That way. It's easy to think about a walk on the Appalachian Trail as a walk in the woods. But in fact, it is a walk on rocks. Lots and lots of rocks.
Yep.
So many rocks. We happen to be on a rare segment that is a walk in the woods with rocks to the side in this beautiful cairn garden that it looks like is made by prior hikers.
Yep.
But those rocks that you're walking on, they are all part of the story of this mountain range. They are a part of its formation. Some of them were formed in early, violent, past mountain building events, like the gneiss you find along sections of the trail, examples of granite and quartz. But much of the rock that was here, part of that early range, has been swept away by water, wind, ice over millions and millions of years. But every rock we pass is part of the rocky history. A wall of rock connecting this range with the Scottish Highlands, mountains in Scandinavia, towering mountains as tall as the Himalayas, It's amazing to think about how a storm like the one we encountered over millions and millions of years can wash away miles and miles and miles of rock. Sorry, I'm not looking at you because now we have roots. When there's not rocks, there's roots. It's always something. And even when there's roots, there's still rocks. It's a tale of rocks. And Kai's ability to navigate them like he's part mountain goat. And I am not. Ugh. All right. Back to my rock walking. Are you taking a rock climbing break here?
Not with this pack, I'm not.
Oh yeah, that's probably true.
Nah, I'm thinking, because, like, this is like the split between the North American plate and the European plate. Split of Pangea is what split the mountain ranges apart. Because how, like, Scotland was part of the mountain range, or the mountain range was part of Scotland's part of it, before the split, and, like, I guess this side's Scotland because the moss represents haggis, and this side is the U.S. because jagged.
Reasons?
Reasons, yeah, reasons. That's a good answer.
Because it's split in two, and
so I guess it's the U.S. during the Civil War. I don't know. It's split in two. Let's move on.
Didn't have a graceful exit of that one, except to walk along the trail.
No, you have a good exit for ending with. I guess this is the Civil War.
I don't.
Yeah, that's what I thought. Let's keep hiking this 8-mile day.
All right.
So we can get to the 12-mile day.
All right, I'll grab my poles.
Thank you, bye. See you at the end of the trail.
Totally looks like parts of Ireland now, here, at least at this part. All right, onwards. So we've taken a little bit of a break from our trail walking today, and I don't know, time walking the trail is a really funny thing.
It kind of just stops happening.
Yeah.
You kind of just like, you wake up when it's sunny and you sleep when it's not sunny. That's how it works.
And everything in between is walking, which makes me think about geologic time and how hard it is for humans to understand the scale of things that happen the processes that happen on our planet, things like mountain building. So the time it took for the Appalachian range to be formed and then to also be eroding away. It also makes me think about how hard it is because those time scales are so vastly different from our own. It's just really hard to understand how the mountains here and the rocks here that we've passed on our trail look exactly the same as rocks in places like Scotland, Scandinavia, Morocco. And it's not just they look the same, it's that they are the same rock. They were formed from the same mountain range. And that's in fact how we know that this was all one mountain range once. Over time, scientists and geologists on both sides of the ocean kept finding rocks that were the same structure, same composition. And it's because, in fact, scientists have identified them as the exact same rock, even though they were split when Pangea split 200 million years ago. They all formed together. So those mountains were all part of the same range. And honestly, that range, it formed in a very normal way, just like most mountains form, right? Continental tectonic plates came together, continental crust got thrust upwards, then those mountain peaks were formed. These mountain peaks eroded away into the gentle rolling hills of the Appalachian Mountains. which don't feel so gentle or rolling when you're hiking up them or down them, but all the same, that is a very normal way for mountains to build. But not every mountain we visited has been formed in the normal way.
That right behind us is Killington, which is where we came from, and it's in the west.
And if you keep going farther west, like 1,900 miles west, you'll eventually hit, say, Rocky Mountain National Park, another beautiful spot that is still 1,000 miles from the coast. And at the coast, you find other mountains, right? The Cascade Mountains, which formed from the subduction of the Juan de Fuca Plate under the North American Plate. Just like most mountains form, right? Just
like the Appalachians.
Yeah, the Appalachian Mountains formed this way, the Andes, Sierra Nevada Range, all forming at the plate boundary. So mountains at the coast, plate boundary at the coast. But the Rocky Mountains are 1,000 miles from that coast.
Let's visit a different hike to show you what we mean.
The Rocky Mountains have majestic views like the one you see behind me. Huge peaks, beautiful glacier-fed lakes. It's just one problem. They're in the wrong place. So 80 million years ago.
Dinosaurs.
Yeah, right. Dinosaurs. Right in the middle of the dinosaurs, there's this massive oceanic plate. It's called the Farallon Plate, and it's right off the western coast. Now, side note, the Juan de Fuca Plate is the largest surviving remnant of this once massive ancient Farallon Plate. Anyway, so 80 million years ago, that Farallon Plate starts to slide under North America, subducting. But instead of going steep the way it's supposed to,
it went flat.
It went almost completely horizontal, like someone slid it under the continent sideways.
Like a spatula.
A spatula?
Spatula.
Like a spatula. Yes, spatulas. Spatula. Exactly like a spatula. And as it went scraping against the underside of the continent for hundreds of miles, transmitting stress far, far inland, past where anything had a right to build.
So the mountains grew from underneath.
The stress had nowhere to go, right? The crust buckled upwards from the inside, 1,000 miles from the coast.
3,000 miles long, peaks over 14,000 feet, built by a plate that was just sliding underneath the whole time.
And the reason it went flat instead of steep, well, we don't really know, but the best guess, it was just young, it was warm, buoyant, maybe carrying a thick section of sea floor on top of it, and just too light to sink properly, so it went sideways instead.
The Rockies exist because a plate was too stubborn to sink.
Yeah, geologically, that is kind of it. A stubborn plate.
You're a stubborn plate.
You're a stubborn plate.
So this plate, it just kept going after the Rockies.
Still pushing, still carrying stress, and still moving east.
And then what?
Well, then it hit something in Utah. There was a crack in the crust that had just been sitting dormant for 800 million years.
800 million?
Yeah, 800 million. Before the Rockies, before the dinosaurs, before complex life on land, this crack just waited.
And something about that crack made a mountain range go the wrong direction. So we've been hiking the AT, and we still are, but earlier we were on the part that intersects with the LT, or Long Trail. And on that part, the AT and ALT eventually split off, the LT going north, and the AT going east, instead of, north-south like the actual mountains go. But
the mountain range, the Appalachian Mountains, like every mountain range in the United States, every major mountain range, go north-south, except the Uinta Mountains in Utah. 150 miles, Kings Peak, over 13,000 feet of elevation. They run east-west. The only major mountain range in the United States that does. That same Farallon Plate that was responsible for the Rocky Mountains is also responsible for the Uinta Range.
So one plate moving one direction accidentally made both the Rockies and the Uintas, but in completely different ways?
Yeah, and for completely different reasons. I mean, that's actually a really good way to put it.
And we wouldn't have any of that if the plates had just sunk normally.
Yep, no Rockies, no Uintas. North America would look completely different.
And nobody knows what else is out there, like how many other ranges exist because of some weird thing nobody's explained yet.
Well, there's one we almost missed entirely.
The Antarctic one?
Yeah, that one.
See, I know. So, we just climbed a considerable distance, I think about 1,000 feet up. And our experience has been often when we get to the top of these little beautiful mountains, this is our view. This is it. Mosquitoes and trees. Oh, and rocks. We have rocks. Sometimes we grab a peek of mountains through the trees. But, all right, we're here. So now we're gonna climb down the other side. And that's what we do, day in and day out. But do you know what? Today, it's not raining. So, pretty grateful for that. All right, onwards now. We'll navigate this. So it's like you can't even see the range up here with this view or lack thereof it, which ironically, there are some mountain ranges you in fact cannot see, believe it or not, at all, because they're completely buried under ice. This one's just buried under trees. Antarctica is the most geologically stable continent on Earth. Middle of its own plate. No active collisions, no subduction, nothing building. If you wanted to design a place where mountains had no business existing, you'd design Antarctica.
Yeah, you would design this. And yet,
in 1958, Soviet scientists doing seismic surveys were bouncing sound waves down through the ice.
Just trying to map out what the bedrock looked like. Kind of standard survey work.
The sounds come back and say, mountain.
Sharp ones, jagged ridge lines, deep valleys. The readings looked like the Swiss Alps, like the way the Appalachian Mountains used to look millions of years ago.
Under how much ice?
4 kilometers. It's a lot of ice.
So there's an entire Alps-sized mountain range that just nobody knew existed until someone thought to listen for it?
Yeah. 1,200 kilometers long, peaks reaching 3,400 meters, the whole thing buried since before humans even existed.
That's pretty insane.
Yeah, and it gets crazier. Think about the Appalachian Mountains, right? We've been hiking on them and how rolling green they are now, but they used to be as tall as the Himalayas, right? The 300 million years of erosion turned them into these gentle, rolling green forested hills. Wind, rain, ice. That's all it takes. Mountains round off, they wear down, they erode away.
The Gamburtsevs look like they just formed.
Yeah, but they're 1 billion years old, maybe older. They should look like Vermont. They should be gentle and rolling and smoothed over.
But they don't.
No, they do not. They are sharp and jagged and craggy and pointy. And then there's this other thing. There's nothing building them right now. No collision, no subduction. Antarctica's just sitting there on a stable plate. There's no reason they should still have any height at all, let alone the height that they have.
So we've got mountains that are too sharp and too tall for how old they are, on a continent with no tectonic activity to explain them, under ice no one could see through until the mid-20th century. So the mountains survived because they got buried.
Pretty much. I mean, if you had asked a geologist in 1957 whether an Alps-sized mountain range could exist under an Antarctic ice sheet, they would have definitely said no. Stable plate, no building forces, any ancient range should have eroded flat millions of years ago. And they would have been right, except for the ice.
The thing that made them impossible to find is the thing that made them possible.
Yeah, it's pretty pretty amazing, actually. And there are probably more just like this, other ranges under other ice, other things we haven't thought to listen for yet.
We just haven't bounced the right sound wave yet.
Yeah, exactly. So we have reached a great moment in the hike, and that is the moment that we are
Done it.
done. We are done, and we are back at our van, and thinking about all the awesome things we saw.
Like this rock. This rock was under a billion-year-old mountain range that's now buried under 4 kilometers of ice in Antarctica.
Well, not exactly. No, that rock's from here. That rock is from here.
Right, but same idea. Potato, potato.
Okay.
The rock was touched earlier, the Appalachians, the Gamburtsevs. They're all the same kind of story. Something massive happened. The evidence is still here. You just have to get outside and know where to look.
Yeah, I mean, the Gamburtsevs, they are still sharp because ice protected them, right? Something hid them for 34 million years, and that's the only reason they still look like mountains.
And the Uintas run the wrong direction because of a crack in the crust from before there were animals on land. The continent remembered wherein it had been broken.
Yeah. And those Rockies, they only exist because a plate was too buoyant, or maybe too stubborn, to do what it was supposed to do.
And these were once the tallest mountains on Earth. A wall of rock from here to Morocco. Gone. And what's left? We just hiked it.
Yeah, we did. Awesome.
You're not kidding.
Oh, come on. Fine. Well, we say mountains are permanent. We use them as a metaphor for things that are permanent. But everything we talked about today, all 4 of them exist because of some accident. Some plate that went sideways, some crack that remembered itself, some ice sheet that formed at just the right moment. All of it.
Mountains are just slow chaos.
Very, very, very slow chaos. Slow at a rate we cannot even imagine.
So next time you're on a hike, pick up a rock. Seriously, because that rock has been somewhere you haven't. It's been under 20 miles of mountain. It's such a continent on the other side of an ocean that didn't even exist yet. The ground isn't stable. It's just moving slowly enough that we forget to notice.
Yeah. But to really understand what's happening here on Earth, sometimes you need to go someplace far out. Like very, very, very far out. Okay, my feet hurt.
I know.
Can we be done now?
Yes.
Can I get my high five? You denied me earlier. Good job, buddy.